In this video, we're going to look at some of the application type questions that you might see regarding the normal distribution. They're mostly just word problems about objects that are following a normal distribution. And so we get some practice extracting some of that information out and converting it to a, trying to eventually get to things in a standard normal distribution question so we can look those up in the standard normal table. This first example, a certain type of battery lasts on average 3.0 years with a standard deviation of 0.5 years. Assuming the battery life is normally distributed, find A, the probability that a given battery will last less than 2.3 years. Let's start with part A here. We're concerned with the battery life, and the battery life is normally distributed. So if I let X be the battery life, we know X is normally distributed, and on average it lasts 3 years. So we know that the mean here is 3 and the standard deviation is 0.5. That's just given in the problem right there. And so we want the probability that X lasts less than 2.3 years. X is less than 2.3. And X is a normal random variable, so we can convert this to a standard normal random variable question. Remember the translation that we made last time when we had these types of problems. Z is equal to X minus mu over sigma. And so this is the probability that Z is less than, in this case, we're concerned with 2.3 minus mu, which is 3, over sigma, which is 0.5. And so we run the arithmetic there. This is the probability that Z is less than negative 1.4. And now we have a standard normal random variable question. And so we'd want to go ahead and look this value up in the standard normal table. Or if we're trying to focus on only using the positive half, we can convert this as well to look at just the positive half. So maybe drawing a picture here will help figure out what area we're trying to look for. Probably that Z is less than negative 1.4. Negative 1.4 less than would be all of this area we're trying to get. So that would be equivalent to finding this area to the right then. And getting that area would require us to look at, the probability that Z is greater than 1.4. And so that is 1 minus the complement. Z is less than 1.4. And so we can go ahead and look that up in a table. What is the probability that Z is less than 1.4? Let's go ahead and let's see, where's our standard normal table here? 1.4. 1.4, right about right about there. 0.8508. So 1 minus 0.8508. 8508. And that is 0. What do we have here? 0.1 minus that should be what here? Need a calculator for that real quick. 1 minus 0.8508. Did I get that right value right? Z is less than positive 1.4. 1.04. 0.8508. 0.8508. So that looks good. So yeah, I guess I must have a small mistake here in my notes. Let me go ahead and grab a calculator. Let's see what we got. So this looks like the desired area then that we want would be 0.1492. 0.1492. 0.1492. Okay. And let's go ahead and just take a quick check. Since we have the bottom half of the table, we can make sure we didn't make any other mistakes here. So let me go ahead and just take a look at what is less than negative 1 point. Oh! I see the mistake I made now. Do you see the mistake that was made? There was a very fundamental mistake. Using the table, z is less than 1.4. This is wrong. I looked up the table incorrectly. Where is 1.4? Not 1.04, 1.40 is down in this neck of the woods at 0.9192. 0.9192. 0.9192. 1.40. 0.9192. So that would be 0.9192. Let me reset my pen here. The arithmetic on that works out to agree with what I originally had then. 0.0808 should be what we are looking at for this. So that is 0.0808. 0808. 0.0808. About 8%. That's about 0.9192. There we go. There we go. That looks good. Part B, the probability that a given battery will last between 2.5 and 3.5 years. So between 2.5 and 3.5 then, we're looking at the probability that X is greater than 2.5, but less than 3.5. Same type of problem. We're really just going to be focusing on using this conversion here. So let's go ahead and punch those numbers in. So 2.5 minus the mean mu, which is 3. 2.5 minus 3 divided by sigma, which is still 0.5, using the same mean and standard deviation from above. And now we have 3.5 minus 3.0 divided by the standard deviation, which is 0.5. There we go. And simplifying the arithmetic here, that's the probability that a standard normal random variable z is between -1 and +1. And so getting the area between here, again, draw a picture if needed to take a look at how to figure this out. That's the probability that z is less than 1 minus the probability that z is less than -1. Minus the probability that z is less than -1. And this first value, we can look directly up in a table. The probability that z is less than 1. 1.0 is 0.8413. 0.8413. 0.8413. And the probability that z is less than -1, we can go ahead and set up another complementary approach there for that. You should try to figure out that probability. That is 0.1587. And so finishing the arithmetic, about 0.6826. 0.6826. And I'll do it for that example. Pretty standard question. Not a lot of extra going on here, just pulling out some of the mean standard deviation questions and asking you to apply it and compute it in that fashion. Next example. This is a pretty standard type of application question that we're going to get. The buyer set specifications for the diameter to be 3.0 plus or minus 0.01 centimeters. So there's a tolerance allowable here of 0.01 centimeters. It is known that in the process of manufacturing, the diameter of a ball bearing has a normal distribution with mean 3 and a standard deviation of 0.005. On average, how many ball bearings are not acceptable? Not acceptable. So what's going to make a ball bearing acceptable or not acceptable then is the diameter. Buyer set specifications for the diameter. So let's let X denote the diameter. Let X denote the diameter, which has a normal distribution has a normal distribution with mean mu equal to 3 and standard deviation sigma, standard deviation is equal to 0.005. On average, how many ball bearings are not acceptable? So what is acceptable? 3.0 plus or minus 0.001. So acceptable would be plus or minus. So you could go from 3.0 minus 0.01 to 3.0 plus 0.01. So acceptable, the acceptable range then would be 2.99 to 3.01. Anything within that is acceptable. Anything within that is acceptable. We want to know on average how many ball bearings are not acceptable. So if it's not within this range, then it is unacceptable. That means we want to find then the probability that X is below 2.99 or above 3.01, the upper bound. We want those two probabilities. And since these probabilities are symmetric about the mean 3, since we're adding just plus or minus the same value, we can actually simplify what we need to look up a lot by using symmetry, that this is actually just twice the probability that X is, this is 2 times the probability that X is less than 2.99. And if you don't see this relationship, let's just draw a picture. Let's go ahead and draw a picture. So what are we trying to figure out? If this is my random variable X, it's a normal distribution. They're always centered around the mean. So this is actually where X is equal to 3, if that's the peak. We want the probability that X is less than 2.99. So, 2.99 is somewhere right here. We want the area to the left there. This area right here. Or greater than 3.01. Well, 3.01 is just as far to the right of the mean as 2.99 is, just in the opposite direction. These are symmetric tails of this distribution. And so if we can find the area of one of these tails, then we can just double that to get the desired area. And I'm going to choose the tail that has the less than symbol, as that's usually how our tables are coordinated. So we want the probability that X is less than 2.99. Let's go ahead and convert this to a standard normal random variable, twice the probability that Z is less than 2.99. You subtract the mean. The mean here again is 3, and divide by the standard deviation, which is 0.005. And so then this is twice the probability that Z is less than, running through that arithmetic there, that is -2. Twice the probability that Z is less than -2. And so we can work to look up what is the probability that Z is less than -2 using a standard normal table. We should find that the probability that Z is less than -2 is about 0.0228. Let's see here. Get my pen back. 0.0228. Twice 0.0228. And so the desired answer is about 0.0456. 0.0456. All right, so about 4.5% of them are not acceptable. About 4.5% of them are not acceptable. It's kind of an interesting question. You are given a certain range of acceptable specifications, and you'll find out that, how many are unacceptable? On average, about 4.5%. Less than 5% are unacceptable. That would mean you are allowing over 95% on average. Typically, about 95% of the ball bearings would be within your specifications. Another common type of question, then, a way to sort of think about applying the normal distribution in some sort of manufacturing process, then, is using this to set that tolerance. Choosing the 0.01 centimeters, for example, saying I want my tolerance range to accept 95% of the products. I don't want to have too many defects. And so what is the allowable tolerance in order to have that? Let's take a look at a last example that will start right here that we will do that. So let's go ahead and write this one out. Gauges are used to reject all components for which a certain dimension is not within the specification. Gauges are used to reject all components for which a certain dimension is not within the specification. We have 1.50 plus or minus D. It is known that this measurement is normal. This measurement is normal with mean mu equal to 1.5 and sigma equal to 0.20. Determine the value of D such that the specifications cover 95% of the measurements. Specifications cover 95% of the measurements. Gauges are used to reject all components for which a certain dimension is not within the specification of 1.5 plus or minus D. Notice the mean here, we have a normal distribution with a mean of 1.5. So we're saying what's that tolerance window so that we are allowing 95% of the measurements through. All right. So that would mean, so again, what is considered acceptable here? Acceptable would be 1.50 plus D would be the upper bound. The lower bound would be 1.50 minus D. That's the plus or minus, right? So that is the acceptable range. So we want the value of D so that the specifications cover 95% of the measurements. And these are normally distributed. And so we want the probability then that X is between this range. That probability needs to be, well, technically at least 95%. We could sort of look at this as a greater than or equal to, but really we have a lower bound of this being 95%. If we set that equal to 95%, then we know we can accept any range above that. So let's take a look at converting this right here. This is a normal random variable. X is normal with a mean of 1.5 and a standard deviation of 0.20. We can convert this to a standard normal random variable question. Remember, Z is equal to X minus mu over sigma. And so what is X in this first case? Well, X is 1.5 minus D. Then we subtract the mean, which is 1.5, over sigma, which is 0.20. And then now again on the upper bound, X is 1.5 plus D. We subtract the mean and then divide by 0.20, which is the standard deviation. And this is equal to 0.95. Let's take a look at what we have inside here. It's some cancellations. So we're just left with D divided by 0.2. Don't forget the negative symbol here on that term right there. So this is the probability that negative D over 0.2, something divided by 0.2 is the same thing as multiplying that by 5. So this is negative 5d is less than z is less than positive 5d. That has to equal 0.95. 0.95. And so we get to this stage here. We're trying to solve for d, and this is starting to look like one of the questions that you've probably practiced before, where you're kind of doing these reverse lookups in the standard normal table. So again, let's think about drawing a potential picture here to see what is happening. Draw your picture. That's roughly centered. That looks pretty good. So there's some value for d, where here's 5d and here's negative 5d. And if we're between this value, then that should be equal to 95% of the area. That should cover 95% of the cases. Minus 5d and 5d are symmetric about the mean 0. And so the area to the left and the area to the right also has to be symmetric in the sense that they have to be the same. Despite my picture being a hand sketch, if 95% of the area is covered in this range, then 5% of the area has to be split evenly between the left tail and the right tail. And so what would be 5% over 2? That would be 2.5%. Has to be split evenly between the left and the right tail. So we know this has to be 0.025, and this has to be 0.025. And so we can use that to find the value of d. From that information, we'd say, well, look, we could try to figure out what d is because we know the probability that a standard normal variable z is less than negative 5d is exactly 0.025. And so we can go ahead and look in the standard normal table and say, well, where is 0.025 in our standard normal table? Or equivalently, you could look for this, or you could say, where is the probability that z is greater than 5d going to be equal to 0.025? Knowing that this is in the positive realm of things, z greater than 5d right there, that would mean what? That would mean the probability that z is less than 5d is 1 minus 0.025. 1 minus 0.025. 1 minus 0.025. And what is 1 minus 0.025 going to be equal to? That's going to be 0. What is this? 0.075. Something's not right here. 9. There it is. 0.975. And so then now we start looking at this, say, where is that in the table? 0.975. 0.9750 is exactly 1.96. 1.96. So in the table, we find probability that z is less than 1.96 is the desired value. And so that would mean then that 1.96 is equal to 5d. And so we divide by 5 and solve for d, and we see that d is equal to 0.392. 0.392.